Hello, welcome to part C of our series research paper reproduction, or what we call replicability. You see, when you're doing a research for your thesis or your project, one thing that you need to do in the literature review or in the methodology is you're comparing your research to the previous researches done, and for you to do that, you need to be able to reproduce the results that were done by other researchers who have published their scholarly work in journals. Then you reproduce their results and you compare them with what you have done, and you make an inference from that. So in this series, we are trying to reproduce this paper once more, the parameter estimation and adaptive control for servo mechanism with control with friction compensation. Now we have done part A, part B, and now we are on to part C. And remember, the main objective is to be able to model at the end of it all, is to be able to model this part right here. Now what we have done in part A and B, we have been able to model the servo mechanisms of the servo mechanism model purely using Simulink model, and also in section 3, the adaptive control design with guaranteed parameter estimation. We'll come back to this one later on. Parameter estimation, I've skipped this part for a zero, but we'll come and model it. But we'll come to it. I'll explain it later. So in another part, this series. Now let's focus on adaptive part B first of all. Adaptive controller design with the rise feedback. Now as you can see here, we have already modeled the error that we are getting, the tracking error, which is Z1. We've already done that in the previous series, and all this gives an estimate of that error that we are focusing, that will be used maybe later in other sections that I will highlight. Now, as you can see, the first equation, how does these equations link up to one another? You see, we have the error, which is already needed because it helps in our feedback, and that then in our negative feedback to try and make the controller follow the desired path, which is xd, given by 0.1 sine 2 pi t. Now in radians, of course, this one's already given in this paper as I was shown earlier before. Now you see the first equation has x1 and x2, that is the velocity, that is the speed and the position of that servo mechanism, and these ones, the phi, the theta 1 up to theta 6, these are what we are interested. Our objective is to calculate those theta 1, theta 2, and theta 3 online to estimate them. Now, without talking very much, I don't want this video to be long. So our main objective here is to be able to, initially was in our model that we ran in the first video, we put U as 1 volts, but it will change depending on the position. Now here, the researchers try to calculate the U, and for you to calculate U, you need 1 over theta 1, theta 2, you add that, the whole of this equation up to, then you subtract the rise, the feedback term, which is again given by this equation here. So in this video, we'll focus on modeling the equation 20 and 21. So we are much closer to finishing this paper. So we need some key parameters. So phi 1, phi 2, these are unknown parameters. So phi I, so I stands either 1, 2, 3, up to I, whichever way you want, can estimate it further. and then we need to, this one will be online calculated or updated with a lump vector, that so it will be lumped, like put together several of them. Okay, so what you just need to focus on is that parameter there that I've highlighted, equation 20 here, and also equation 21 for the rise term. So this is what we are focusing on. So first of all, the output is u, of course, that u. So we start with the simplest one. So we need this one we multiply after doing the inner modelings of this equation. What do I mean by inner modeling? So we have phi 1 and that 2. So we start here, we add them. This one will come later. All these are, so this one starts from here up to here. It's an addition. Then we subtract these two, we add them, and then we add the fourth term, the theta term, the fifth, sixth, and seventh. So we need like almost how many some signs, arithmetic signs. So we need like 1 right here, 1, 2 here, 3, 4, 5, and 6. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So we need 6 of them. Correct. Now the next part we want to do here is start. I'm trying to make this equation clear. So we start by having a phi 1, we add it to phi 2, of course. Then phi 2 we add it to phi 5. Then we multiply by xd. Multiply by xd, so this is the xd that comes inside. So to get this xd, but we need to multiply by xd dot. So we take the derivative, multiply, we get that. Feed it with our summer block. This is just as normal addition, that you can add several signs that you want. So the next bit of this one is to take this bd times xd, the same one, multiply them, beta 1 times xd dot, and then we pass through the tan h. After doing that, this becomes our positive, so it goes there. Then we subtract the second one, be beta 2, we multiply by xd dot, pass it through that tan h, comes to the subtract sign, negative part. After that, we multiply all of them by theta 3, which of course they will come from outside. Then everything else we add according to here. The next part, we take this beta 3 times xd dot. So beta 3 times xd dot, we pass through tan h right here. After that, beta 3, sorry, this is beta 2 I was referring. This is beta 3 times x2 dot, pass through tan h, multiply by theta 4 right there. The next one is we take it's xd dot dot. So we do the first derivative, then we do the second one. After doing that, again we get now x dot dot, we pass it through the addition part, and then 36 is just 36, comes from outside, and then of course we add the rise term right there. After doing all of these, we multiply by 1 over theta 1. So of course online estimated. So I put this one here because I'm just with an initial condition of 6. There it's also given because during the start this might be 0, and you see if we get a 1 by 0, that's a 0 division error. Matlab throws up a huge error real quick. I'll go through the errors of this. So one of them was to use this one, so that at the rate transition block, so that at initial condition I specify at 6 and pass it along. So again, all these beta 1, beta 2 are already specified initially. XD is already created in the initial in the previous video. Any other term that I've used that is undefined, I don't see. And then after that, we take the transpose, the one over the signal that is coming in. Then of course we multiply it by u, by our u now, by our signal, by our addition, the whole of it, we get u outside. Then we come to the right term. So let's go through the equation for the right term pretty quickly. So for the right term, we need ks plus 1 multiplied by z2 minus ks plus 1 over z2 at 0. So that means all this term, it means that we need to make sure that at 0, this one and this one, they cancel each other out. So it's that at 0. So that's what it means by having the same term. So we need z2 at 0 basically, so that it can remove the effect of maybe if this value was, if this evaluation was instantiated at let's say value, let's say 5. So we need to make this one 5. Basically what you need to do here is just implement this one, there's no harm, and also do this, the integral from 0 to t ks plus 1 k2 z2 over sigma then lambda, lambda sine function of z2 sigma in that. So for the last time, what we need is ks. Of course, you're given ks 100 in the equation. I'll show you what else. Z2 we calculate from the tracking error and sliding in the series video we had to for part B, and also get z2. So no worries, this is the new term that is introduced. Then ks, of course, and that plus a constant 1. So we start here. So we start here, we add 1, then we multiply by z2, of course, that comes there, we get that one. Ks plus 1, we add that one, we multiply by 2, 3 multiplication by k2 z2, we get our answer. We add, we take the sine of z2, after that we multiply by our lambda, which is again something bigger than greater than 0, so I choose a value 10 for that matter. After adding everything, we integrate. Of course, the initial condition at 0, at t is from t0 to that, I'll put it at 0. Then of course we add, then we get our right term. This right term we feed it to equation 20 here now as it's used. So that's pretty much straightforward. From now on, proceed to the updating law and probably be able to finish this paper. Now there are some errors which I'll show you at the end of the videos and how to overcome them. For example, I've introduced the rate transition to be able to prevent that zero division error, so that at 0 everything is not 0 for this one, because Simulink has some weird responses to that maybe. And then we have some algebraic loops, of course, you need to take care of them. So as you can see, these are complex equation. So we are bound to get those errors, but we'll go through them and show you how you can be able to debug and see where the problem is. So with that, let's see you in part D of this series, the next part, where we'll be able to model the equation 24, which is the last one. With that, have a great time. See you in the next one. Like, share, and subscribe. Bye bye.